Okay, this is going to be your first lecture, and I'm going to go ahead and keep my video on so you can see that I'm a real person here. I normally, for most of the lectures, will actually turn off the video, and that's mainly because once I go into the presenter view, I can't tell whether or not this little screen of myself is actually taking up some of the view of your slides. So again, I'll leave it on for today because my slides aren't quite as busy. But in future lectures, I will have that off just so that you can see the entire slide. But I usually will do weekly announcements for you, and I will usually have my video on for that so you can again see that I am a real person behind these lectures. Okay, so let's go ahead and get started for today. Again, these lectures will typically hopefully be around 30 minutes. And I usually will start with the objectives. So today this lecture is called Thinking Like a Scientist. And the idea behind this lecture is to give you an idea of how science is done. So again, science is a study, and it's based on a foundation of certain principles. And so I want to give you an idea of what those principles are. So at the beginning of each lecture, I will have the objectives of what you should learn for each day. And so today we're going to talk about what science is and how it works. We're going to distinguish between two basic forms of science and two basic processes for science. So we'll call that descriptive-based science versus hypothesis-based science. And when we talk about hypothesis-based science, we are going to list out these steps for the scientific method, which is, again, what we're going to use in our hypothesis-based science, that series of fundamentals for that. We're also going to explain how to design an experiment to actually test a hypothesis. And then once we actually do that experiment, we're going to talk about how scientists make a claim, provide evidence, and explain their reasoning. And then at the very end, we're going to compare and contrast science with religion. So let's go ahead and get started. So we're first going to talk about what is science. And so science is a collection of facts and theories about nature. It's a process by which we use to answer questions about nature and the natural world around us. And so this is a systematic process that we use to be able to describe the natural world. And there are two main types of science that are performed. We can do descriptive-based science, and then we can also do hypothesis-based science. Now, as you can probably guess, descriptive science oftentimes will lead to hypothesis-based science. So when we talk about descriptive science, our descriptive science aims to observe, explore, and discover new things. And so when we're doing descriptive science, we might be searching for new drugs in the Amazon by searching for new plants. We may be trying to look and identify new species of plants or new species of animals in the Amazon to identify whether or not there are species that are undiscovered out there. And so this is more descriptive science. We are looking to just observe the natural world, explore it, and discover new things. And so there is a very important role for descriptive science in both biology and ecology. And sometimes I feel like courses can sometimes look negatively upon descriptive science, but this descriptive science is very important for oftentimes hypothesis-based science, because this descriptive science may lead to a hypothesis-based science. So for example, if we were to use descriptive science to discover a new species of plant in the Amazon, we may say, well, this new species of plant was used by these indigenous people, and they were using it for medicinal purposes. So then we may actually take that plant, and this was actually what I did for my graduate research, and then we can actually look at some of those plant compounds within that plant, and then we can actually test to see, using hypothesis-based science, whether or not that plant species does in fact have some medical potential. So again, descriptive-based science is very important, just as important as hypothesis-based science is. So I've been talking about hypothesis-based science, but you may not know what that is. So hypothesis-based science, let me go back here. Hypothesis-based science is where we begin by either asking a question or making a statement called a hypothesis, and then developing an experiment to test that. So for example, in this image here, you may have a question: is this new pesticide that this individual is using safe for use? Okay. And then you might develop an experiment to actually test that. Or you could actually start with a hypothesis, which is a statement about the natural world. And so you may say slow moving is more polluted than fast moving water. But to make that statement again, we're going to need to test it. And that's where hypothesis-based science comes in. So let's talk a little bit about the scientific method and then how we would do this process, and then we'll go through some examples. So when we do the scientific method, we oftentimes start with some type of observation about the natural world. So you may make an observation that you were at a pond with slow moving water and you were at a river with fast moving water, and the river with the fast moving water looked cleaner to you. Okay, so that would be your observation. So your question then may be, is slow moving water more polluted than fast moving water? And that would be your question, right? And then your hypothesis is going to be a statement that, again, usually is explaining some phenomena about the natural world, or it also may be just answering your question that you originally had. So in this case, we may say, the hypothesis is that slow moving water is more polluted than fast moving water. And so then we can go ahead and design an experiment to test this. And then we'll make a prediction of how we think the outcome of this experiment will be. So a prediction is basically a very specific statement after you've designed your experiment, stating what you think is going to happen in your experiment, what the outcome is going to be. And then what you're going to do is you're going to go ahead, design that experiment, okay? And we're going to talk about how you're going to design that experiment to be most effective for hypothesis-based science. And then you're going to go ahead and record the results of that outcome. And then you're going to go ahead and make a conclusion based on those results. And in your conclusion, you are going to look at, did your results actually match your prediction? Okay? And if they didn't, then you're going to go ahead and go back and revise your hypothesis. And then you can retest. So oftentimes, and I just actually read an article about this, oftentimes scientists won't publish their information if the results didn't support their hypothesis. And that's actually really unfortunate, because that information is important information so that someone else doesn't repeat this experiment if it's unnecessary. So if you end up having an outcome where in your conclusions, your results were, your hypothesis was rejected based on the outcome of your results, this is important information. So that way then others can use that information and then make, again, new hypotheses based off of that information. So again, an outcome that doesn't support your hypothesis is still very important, because science, I like to think of science as this kind of big loop, and we're constantly coming up with new information. We may have a hypothesis, and this one experiment supports our hypothesis, but then we develop some new experiments that come along and show that not every situation will we get the results that will support that hypothesis. So science is always evolving. I like to think of science as this revolving door, not this door that opens and closes, because again, we're always updating and revising our hypotheses based upon the information that we have available to us at that point in time, and the also technology that we have at that point in time to be able to perform the experiments. So again, that's how I like to think of science. Now, science is social. And what this means is that scientists are constantly working with other scientists. So for example, again, even me as a biologist, I constantly am attending conferences. I will attend a conference each year to update myself on the information that is in my field. And it's nice to have other scientists all in one room being able to share that information on your field of study. So scientists are constantly working with other scientists. We're constantly having these conferences. And the reason that your instructors have to attend these conferences is because this is how we gain information about the most current research that's ongoing in our field. And so you can see here is a biologist that's sharing her research at a scientific conference. And scientists will also publish their findings in what we call peer-reviewed journals. So when scientists are publishing their information, this information is not just willy-nilly information that's like published on the on the web that isn't necessarily checked by other people in their field. A peer-reviewed journal is going to be a journal that has a panel of peers, meaning there are going to be people that are in your field that understand your research and how it should be conducted. And they actually are going to go through your research kind of with a fine-tooth comb and look at your research, make sure that it's sound research and that the data that you are presenting appears to be sound data. So when scientists publish their findings in peer-reviewed journals, usually, again, this information, it has been kind of fact-checked, if you want to say. And so I oftentimes, when I am looking for information in my field, I will go to peer-reviewed journals because I know that that information has the kind of most sound information at this point in time. Now, scientists will present these findings just as I talked about at conferences, and that way then we as scientists can go to these conferences and stay updated in our field of study. And again, scientists communicate these findings as well to the public, oftentimes again through media outlets. Now it's much easier because we can do it through podcasts, we can do it through social media, and so today there are much better ways to communicate our findings to the public than it used to be. Even just 20 years ago when I was a new biologist, things were very different then. There wasn't the communication with the public that we have today. Okay, so let's talk about the difference between a hypothesis and a prediction. And then we're going to kind of go through some examples eventually here of how we do the scientific method. So a hypothesis, again, is a possible explanation or cause of some type of phenomenon. So for example, you may make a hypothesis here about this observation that you make here, stating that darker objects get warmer because they absorb more light. And so that's a hypothesis. You're making a statement that includes a possible explanation of a phenomenon, okay? Now, a prediction is going to be a little bit different. A prediction is a statement about what is likely to happen if your hypothesis is true and you do an experiment to test it, okay? So, for example, if your hypothesis is true and you shine a light on these two objects to test to see if your hypothesis is true, then your prediction would be that the darker one will be warmer than the yellow ball, which is lighter, okay? So that's the difference between a hypothesis and a prediction. A prediction is really more of a statement about what's likely to happen in an experiment if your hypothesis is true. Now, an experiment, when you talk about experiment results and conclusion, our experiment is going to be the method that we use to test our hypothesis. So again, sometimes it's tested just by gathering more data. So again, you may look at this light and you may, take a darker ball, maybe it's a black ball, maybe you might try a blue ball, okay, and test it against these lighter color balls. So again, maybe a yellow ball, maybe a white ball. And you may document the temperatures of those balls after a certain amount of time. So that would be your experiment, right? Your methods that you're using to test your hypothesis. And then your result would be the data that you've collected in this experiment or test. So again, your results here would be a series of a table, maybe a table or tables that are documenting the differences in your temperature of the balls after a certain period of time that are dark versus light. And then you can make a conclusion based on whether or not your hypothesis was supported. So did your results, when you make your conclusion, did your results actually match your prediction that you made? And so again, that's an important part of making those conclusions. So in this case, you may say, yes, my hypothesis was supported because in fact, the temperature of our darker shade balls was higher than the lighter shade balls, okay? And you can back that up and support that with your actual data. Now, when you come up with a hypothesis, okay, your hypothesis, there's a couple requirements for a hypothesis. And this is important because this is kind of a big foundation for science and how we do science. And one of the big ones is that your hypothesis must be testable. Okay. And it must be potentially falsifiable. So what does that mean? It means it has to have the potential to be tested and shown to be false in that test. Okay. So I say potential. It doesn't have to have the outcome of being false, but it has to have the potential of being shown false in that experiment. So there must be a way to test it and to show it's not supported, or that, again, your hypothesis is supported. But there has to be this potential of showing that it's not supported, meaning there has to be, again, that built into the experiment. So again, if you have something that is not testable, not potentially falsifiable, then it's not a hypothesis. And this will come into play at the very end when we talk about the differences between religion and science. So again, if you state that you had a certain religious experience, the challenge is that you can't make a hypothesis about this because, again, in science, a hypothesis has to be testable and potentially falsifiable. So this, again, is very important because there are going to be things that are outside of the realm of science. So right now, what happens to us after we die? And right now there is no way for us at this point in time, based on the information and the technology that we have, for us to test this. So there is no way for us to be able to come up with a hypothesis that can explain what would happen to us after we pass away. And so again, this is where we have limitations for science. Science has these limitations, and this is a hard limitation for science. Hint, hint, this probably will be on an exam at some point. So again, that hypothesis must be testable. The hypothesis must be a statement, not a question. So you can originally come up with a question in this process of the scientific method, but your hypothesis needs to be a statement, and that statement may be an answer to your question, but it needs to be a statement. And then the third thing is that this hypothesis must be about natural causes, the natural world and natural causes. It cannot be about supernatural causes. It's, again, outside the realm of science, the limitation. So you may say that you saw a ghost in your house and that you have a ghost that is haunting your house. But there is no way for us to test this. Again, it is outside the realm of science. It is what we call supernatural. And so it's not testable, and it's the limitation. It's the boundary of science. It's outside that boundary. Okay. So hopefully that helps explain a little bit about how we do science. So let's talk about really quick, which of these is a hypothesis? One, my computer will not turn on. Okay, so that's a statement. Okay, plants grow better with fertilizer. There's a statement. Guardian angels guide my life. There's a statement. And then, why do I have a headache? Okay, so the easiest one to rule out here right away is, of course, this one. Why do I have a headache? Because that's a question. So right away you can say, oh, that's not a hypothesis. Okay, so let's go to 1, 2, and 3. Let's first talk about my computer will not turn on. Okay, now this is a statement, but this is actually more of an observation, right? It's not giving an explanation for a phenomenon. The phenomenon is that your computer won't turn on. A hypothesis would try to explain why your computer's not turning on. So again, this first one is actually an observation and not a hypothesis. Now the second one here, plants grow better with fertilizer. Now that one is a statement that is trying to explain a certain phenomenon. So is this a hypothesis? Yes. If you picked number 2, you are correct. That is the one that was the hypothesis. Now, if you chose number 3, guardian angels guide my life, again, this one falls back to this last limitation here. Supernatural causes can't be tested. So again, this is not, there's no way for us to test this at this point in time. And so because of that, that can't be a hypothesis because it's not potentially testable and it's not potentially falsifiable. Okay, so hopefully that explains hypotheses. Now let's talk about what a theory is. So theories, oftentimes if you hear the word theory used, it oftentimes is some kind of idea about something that you have that is, you know, maybe true, but maybe not true. Our theories are kind of like, oh, I have this idea. But this is very different than the word theory in science and the use of scientific theories. So a scientific theory is actually just the opposite. It's not just some random idea that you have. A scientific theory is a plausible explanation for a wide range of related phenomena, meaning it is an explanation that will explain many different phenomena out there. And I'll give you this example of gravity, this theory of gravity, in just a minute. So again, a theory is going to usually be supported by lots of evidence, meaning at this point in time, all of the evidence supports this idea, okay, and this explanation. And it's not a guess or a hunch. It's not a personal opinion. Again, this is something that has been tested over and over and over again, and all of the evidence is supporting this hypothesis, and we've elevated it to a theory. Now, again, it's oftentimes made up of many supported hypotheses and facts. So let's look at an example of this. So is gravity a fact or theory? So let's look at a couple different facts. So for example, when we talk about gravity, we know that we have this fact that objects on Earth always fall at a certain speed. Okay, so that's a fact. We also know that more massive objects are going to exert more gravity. Okay, that's a fact that we know. We also know that gravity causes planets to orbit around the sun. So we have all these facts, right? And then we can list more and more and more facts about gravity. Now then, there are multiple hypotheses that we have about gravity. There's a hypothesis that gravity moves through space as waves, more like just as light and sound moves as a wave. There's a hypothesis that gravity causes space-time to bend. Okay, and that's a kind of a more interesting, newer hypothesis about gravity. And there are all these other hypotheses about gravity. And so because we have all of these facts and all of these hypotheses right now that support this theory of gravity, at this point in time, again, our theory of gravity is elevated, not just from a hypothesis, but to a theory of gravity, because all of this evidence, all of these facts, and all of these hypotheses support the theory of gravity at this point in time, okay? Now, again, if information comes along, okay, later on, or we develop new technology that negates this theory, then we will update, right, this scientific information. But at this point in time, a theory is as close as we have in science to scientific fact. So, for example, when we talk about evolution by natural selection, okay, in science, evolution by natural selection is a theory. And the reason that it is a theory is that all of the hypotheses and all of the facts that we have in science at this point in time support the theory of evolution by natural selection. So we'll talk more about that if you don't know what it is, but we'll get into that a little more later. I know I'm getting a little off topic here. A scientific law is a statement. It's different than a theory, a scientific theory. A scientific law is actually just a statement that describes some aspect of the universe, and it always applies given the same conditions. And this rarely is the case. We rarely find these laws in biology. We mostly find them in physics. So, for example, a scientific law would be that objects in a vacuum always fall at 9.8 meters per second on Earth, okay? And that's true for everything. Any object that you put in a vacuum will always have this outcome. Always, okay? And so that is a scientific law. Now, again, laws are more rare in biology because biological organisms are living organisms and they don't always follow this same set of rules. And that's because things adapt and evolve and change within biological organisms. So again, scientific laws are much more common in physics than they are in biology. Now let's talk about, as we do experiments, let's talk about variables. So experiments oftentimes deal with variables. And this is anything that we can change and alter. And there's two important variables that you have to know, and I want you to be able to identify. And that is an independent variable. That is the variable that you are manipulating as the experimenter. And then that usually causes a change in an outcome that you're measuring, okay? And that's the dependent variable. The dependent variable is going to change in response to the independent variable. So your dependent variable is what you are measuring at the end. And my hint for you on how to remember this is that the dependent variable, what you're measuring, is going to depend, hence the name dependent variable, depend on your independent variable, what you're actually varying. So let's look at some examples of this. Okay, so let's say you're designing an experiment and you make an observation that your houseplants aren't growing, okay? And your question may be, does fertilizer improve plant growth? And your hypothesis may be that fertilizer does in fact improve plant growth. And so if that's your hypothesis, then you need to come up and design an experiment to test your hypothesis. So you need to come up with your independent variable. And in this case, your independent variable is pretty easy here. You would vary fertilizer, right? That's what you would vary. So that's your independent variable, fertilizer. And your dependent variable in this case is plant growth, what you're going to be measuring. And that's going to, in this case, in your experiment, depend upon whether or not it has this independent variable, fertilizer or no fertilizer, okay? And then once you design that experiment, you're gonna go ahead and come up with a prediction, okay? You're gonna predict what your outcome will be. So maybe you design an experiment where you're gonna take a bunch of these plants and you're going to plant the seeds. okay, all at the same time, give them all the same amount of water, give them all the same amount of sunlight, but half of the plants you're going to get fertilizer and half of them are not going to get fertilizer, okay? And when you design an experiment, your ultimate goal is to only vary one variable, only vary this one independent variable, and everything else is going to stay the same. So for example, in this experiment, you want them all to have the same sunlight. You want them to all have the same amount of water. You want them to be exposed to the same temperature. So again, you want to keep all of these other factors, all of these other environmental factors the same, except for this one independent variable, fertilizer, okay? And so in that experimental design, it has to be what's called a controlled experiment, meaning you control for all the other variables except for that one independent variable that you were testing. Now you must have a control group, and that control group is the group where the independent variable is not altered, meaning that in this case, you would not give any fertilizer. So your control group would have no fertilizer, and then your experimental group would be given fertilizer. And then, of course, you want to have a large sample size. You know, if you just have 2 plants and you give 1 fertilizer and 1, you know, as your control, you don't give fertilizer. Let's say that for some reason, this plant had a disease and you didn't know it, and it didn't grow very well because of that disease. Then again, that experiment wouldn't be very valid because you didn't have a large sample size. Larger sample sizes will accommodate oftentimes for these variables that we just don't know are in our experiments, okay? So again, we're dealing with living organisms, and these living organisms are going to grow at different rates on their own anyway, okay? So we have to account for those slight differences with large sample sizes. So the larger the sample size, usually the more accurate your experiment is. And so again, in this experiment, does fertilizer improve plant growth? You're going to look at your outcome. So again, you know, you may after, I don't know, 6 weeks or 8 weeks, decide to go ahead and measure the average height of these plants. And so you can see here's your control group with no fertilizer, and here's your experimental group with fertilizer. And so in this case, now you want to go ahead and look at the evidence. And in this, you can actually find at least 3 pieces of evidence that would support your hypothesis. So the easiest one is to look at the average height, right? So the average height for this group is 12 centimeters, and the average height for this group is 23 centimeters. And you'll see you have these outliers, but again, by having a large sample size, we can kind of accommodate those outliers, right? So overall, on average, the group that had fertilizer, again, had an average height that was larger. But you could also look at, the number of leaves that each plant has, okay, and say, okay, well, look at the group with fertilizer has larger leaf biomass. You have more leaves, you have larger leaves. So you can look at leaf biomass. You can also look at the stem biomass. So here you can see that the group with fertilizers had not only, again, larger stems, but their stems were more branched and there was more stem biomass. Okay? So those are things that you can all look at. Now, after you've done your experiments, you can go ahead and come up with a claim. You're going to provide the evidence and then explain with some common reasoning. So scientists typically will make a claim, they'll provide the evidence, and then explain their reasoning for that evidence. So a claim is just a statement about the results of an investigation. It's going to be a statement that answers the question that you originally had. What can you conclude from, again, your experiment? And then you're going to describe the relationship between the independent and dependent variables. So in this case, again, if you're going to make this claim that the group that was given the fertilizer did in fact have plants that grew larger than the group that was the control group, you can again do this and explain that relationship by looking at the independent variable, the fertilizer, and how it impacted overall plant height, overall plant leaf biomass, overall stem biomass, and stem branching. Okay, so you can look at all of those relationships. Now again, once you make that claim, you need to back up that claim with your scientific data that was used to support that claim. And that scientific data obviously needs to be sufficient. You need to have enough evidence to support your claim. So again, that's where your larger sample size comes in. And then obviously that evidence needs to be appropriate. It needs to be the right data. So again, you want to leave out any unnecessary information. So in this example, you don't want to just talk about this plant and this plant here, because again, those are your outliers. And so you want to, again, make sure that the evidence that you're using is appropriate information. It's the right data to support your claim. And so again, when you have this evidence and you're using this evidence, it can be both quantitative, and quantitative is, of course, going to be based on numbers. It's an outcome that you can measure. So again, in this case here, obviously this is quantitative data, plant height, because it's something that you can measure. You could even measure plant biomass in terms of the leaf biomass here versus the leaf biomass here, and that would be a weight measurement. So again, those are all examples of quantitative data that you can measure. Now, there's also qualitative data that is important as well. You can use your senses. So you may look at the leaf color on the group with fertilizer and compare that to the leaf color in the group with no fertilizer. So again, that is some qualitative data that you can look at to say, does this plant look healthier? Because here maybe the leaves were yellow and maybe here the leaves were very green. So again, that's qualitative data that you can use. That's using your senses, your sense of sight, your sense of smell, sense of touch. The leaves may feel different, okay? So again, those are all things that you can use, and you can use both. You don't have to just use quantitative or just qualitative. You can use both. And then based on that information, again, we can come up with the last step in this process, which is reasoning, how the claim is actually tied to the evidence. So when you're reasoning, you're going to show how or why the data count as evidence to support that claim. This is going to justify why this evidence is important to this claim, okay? And this is going to include some scientific principles that are related to that claim. So again, you might be talking about fertilizer, and you may say, well, look, this fertilizer we know has been shown to have certain nutrients in it that plants use. So those nutrients are supporting that plant growth, and that's supporting, again, the outcome that we saw in the experiment. Okay? So let's just go through kind of an example that you might do, again, using this kind of deductive reasoning and using these scientific principles just in a general case here. So you may see this site, you may look at this site out here, and you may go, well, is it safe for my kids to play in this water? Okay. And so you might make some claims that, you don't think that this water is safe to play in because here it just looks dirty. Okay, so maybe the claim is that it looks dirty. And so again, then you might use some actual evidence, some facts that you can see about this. So again, you might state that there is this dumpster here, and this dumpster, when it rains, is leaking, again, those juices from the dumpster into this body of water. Or you might state the fact that these people are all wearing hazmat suits, and typically hazmat suits are only worn in a case where people are trying to prevent things from being absorbed into their skin. So again, you can kind of go through this idea of making claim and using evidence and reasoning to answer this question, is it safe for my kids to play in the water? So again, you know, if it were me, I would be making the claim it is not safe for my kids to play in this water. The evidence that I have is, one, that the water actually qualitatively looks dirty. There are pipes in it, so that's a qualitative observation. There's a dumpster nearby, just like we talked about, and it can leak, again, some of those juices from the material, the garbage that is in the dumpster. And then there are 6 people in hazmat suits at the edge of the water. And typically, again, those hazmat suits are worn when toxic chemicals or pathogens are present. So again, here's the evidence, and then I kind of jumped into the reasoning of why that evidence is supporting our claim. So again, dirty water can have pollutants that harm humans. Pipes often carry hazardous chemicals. This is all reasoning as to why that evidence is supporting that claim. Dumpsters can leak garbage juices that run into water. Hazmat suits are worn when toxic chemicals or pathogens are present to prevent us from absorbing them into our skin or our mouth, right? Because they could potentially cause disease. So again, this is how you would use some of this science, some of this deductive reasoning in your everyday life to answer a very simple question like, is it safe for my kids to play in this water? Okay. Now, really quickly, we're going to talk, this is a little longer than I wanted, but we're going to really quickly talk about science and religion. We already kind of talked about this, so I'll go over this pretty quick, but science, again, deals with natural phenomena. So again, remember that science is going to be dealing with things that are testable and potentially falsifiable. And this depends on observations and measurements that others can verify, okay? So hypotheses must be testable, just like our fertilizer experiment, right? And this is very different from religion because, again, this is not testable, potentially falsifiable statements that can be made that other people can verify or test. So, for example, you know, you may have had this religious experience and you feel for yourself for it to be fact. However, it's just not testable. Again, it's outside those limitations of science. It's not saying that we're, you know, in science, we're not saying that religion is not true or one religion is, you know, true and one isn't, because it's outside the limitations of science. Again, science has these limitations and that's outside of it because it's not talking about a natural phenomena. So there's no way for us to test whether or not that phenomena or experience that you may have had with religion would happen for another person because there's no way to test that. We can't, again, do that because it is bound by these limitations of science, of what we have at this point in time to be able to test and experiment, right, with these hypotheses. So that's not to say that, again, you know, in the future, we don't develop technology that is able to test that further. But at this point in time, there is no way for us to test religion within the boundaries of science. So again, and this is just like I like to tell people, when you're in science, you have to put your science hat on, okay? And in a science classroom, and remember that you are bound by these boundaries and limitations of this discipline, what science is. Now, again, in a religion class, we're not, again, bringing science in because religion is bound by its own boundaries, right? And so, again, they're different disciplines, right? Just like if you're in a math class, you're bound by those boundaries for math, okay, as a discipline. Same with English. You're bound by those boundaries of grammar and spelling that are, again, in that discipline, okay? So again, when we talk about science, we don't include religion because, again, it's just outside the boundaries of science, right? So if you have any questions, please feel free to email me, and then I will see you for lecture 2.